Hi guys, welcome to yet another Word Electronics repair video. So I have this which was sent to me from the UK. It's not what it says on the box at all, it's something to repair. A subscriber contacted me and said that they had this. It comes from a health centre or large doctor's surgery, and on the building they have a big clock tower with the four faces, like Big Ben but probably a bit smaller. Actually that's a misnomer anyway. Big Ben is actually the name of the bell, not the name of the clock tower, so there you go. But this comes from a probably slightly less ostentatious clock tower with four clocks on, and they had some sort of power surge. It caused a lot of problems, a lot of computers and things went down, and this blew the fuse, and they replaced the fuse but it's not working. So that's what I know about it. So let's have a look to see what we have here. Obviously I don't have access to the clock tower. So there's four connectors, I can see that straight away. Four connectors, on or off. They're all set to, two of them are set to on. Maybe they only have two clocks on the clock tower. Yeah, half a Big Ben. Couple of fuse holders here which I will check. There's another fuse here. I'm not sure which fuse actually blew. I could ask them. And really that's, you know, there's not a huge amount on this. This is clearly a bridge rectifier, and I better zoom down a little bit, hadn't I, so you can really see. Okay, that's a little bit better. So we have fuses coming in. This is the live and neutral. This is marked on here, earth, ground. This, I am assuming, yes, it says primary and secondary, pri and sec. So this is going to be a linear transformer. Does it have built-in fuses? Can you see here where it says it's more like there's a fuse on either side as though it's built into this. Then we have a bridge rectifier down here. We can see that one. Yeah, so it says AC, AC plus and minus. So this will be converting AC to DC. But we have another one down here. Ah, this is not a bridge rectifier. AC load control. This is some sort of, I'm not sure, solid state relay or something like that, maybe. Probably is. So this has probably got a bit like an Opto Isolator but more powerful. So it'll have almost certainly an LED in here, infrared, shining onto a photosensitive transistor, and probably switching a Triac or a Thyristor. So a Triac and a Thyristor, these are basically, they have a low voltage gate which you put the signal on. When you turn it on, it switches on. Thyristor will pass only in one direction. Imagine it like a switchable diode. In fact, let's not imagine it at all. Let's have a look to see what a Thyristor is and a Triac, because you might not be that familiar with them. So here is the basic principle of a Thyristor and a Triac. So with a Thyristor you have AC coming in, usually mains voltage, 240 volts, 220 volts depending where you are, 110, yeah, and that goes to the Thyristor. So the Thyristor is basically like a diode, and this is the load, and this goes back to the 220 volts AC. So this is your AC input. Okay, so that is just a diode, and this circuit, this would, on the positive half cycle, would feed current to the load, and on the negative half cycle, because the diode, it only conducts one way, it would block. So coming into the load here, you would have each positive half cycle of the mains. Okay, so with a Thyristor we have an extra pin called the gate. Because this is basically a diode, this is the cathode, this is the anode. Okay, so we can use the gate to switch the Thyristor on. And this is the common circuit that's used for switching AC. So we have another diode in here, Okay, and we have from here a resistor up to here. Okay, we have another resistor down to here, which, if you like, this we could call it hot ground. Yeah. Okay, and the way you would normally switch it is by switching the voltage at this point. So because this is all connected to the mains and we almost certainly want to control it from a low voltage circuit, here we would use an Opto Isolator. So here is our Opto Isolator. Okay. And then we would have the diode of the Opto Isolator. Okay. With a resistor in series, and this is your switching device, whether it's a microcontroller or whether it's just an oscillator or whatever we have. Putting pulses in here can switch the LED on, which shines onto the photo transistor, so when the LED conducts, it switches on, it glows, it shines light onto this transistor, and that pulls the voltage here down and makes the circuit switch. So this is our Opto Isolator. Yeah, and I've drawn it wrong straight away. So this wouldn't help because look, this photo transistor is connected to hot ground. I've also connected our diode to hot ground, so we have no isolation from the mains. Yeah, this here goes to our safety ground. Yeah. And the microcontroller sending pulses in here is also connected to safety ground. So when you put a pulse on here, unlike the LED, as I've just described, it switches the thyristor on. But when the pulse stops, the thyristor will not stop conducting straight away. With the thyristor, once you trigger it, you switch it on, it will continue conducting until the current passing through it drops to 0. Now with an AC signal that will happen because there is your AC half cycle as I've described. If we use a controller to detect the 0 crossing point of the AC here, yeah, here. If we detect that point and we switch the thyristor on at that instance, it will start to conduct here, okay? And it will conduct during this half cycle. Now we can switch it back off again. It doesn't matter where we switch it off, anywhere in here, because it will keep on conducting until it comes back to here where the cycle goes negative, where it passes 0 and it will switch off. Okay? For example, we could do this so that when we switch a switch on, we don't get a click through the speaker, say on an amplifier or something similar when you're switching a switch on, because we switch it on when it passes 0, so at the point we switch on no current is flowing. So that's one use for a thyristor. Another thing we can do with a thyristor, draw the negative half cycle, is we can switch it on at a certain point during the cycle. So if we send the pulse here to switch it on, at the point when the mains voltage is its peak, it will actually conduct for this half cycle until it switches off. Yeah. So now we only have that much of it coming through, half of the waveform. Yeah. And by moving the switching point, I'm sure you can see. Sorry, postman delivering some more things to repair. More videos coming up, yeah? So as I was saying with this, by altering the switching point, effectively we could make a light dimmer, for example. So we could have it on full brightness, the less of the waveform it dimmer it gets. Yeah, we could make effectively a light dimmer out of this. Okay? So that's what a thyristor is. Now you can see that the thyristor only conducts one half cycle. So even when it's conducting for the full half cycle, if you had a light bulb attached to this, effectively you would have half brightness because the other half, the negative half, is not conducting. So this is where we use a triac. So a triac is basically the same thing as this. Okay, but it effectively has, I'll try and draw the symbol correctly. It has effectively diodes in both directions. Look, I made a mess of it, didn't I? I made a mess of it. Let's go again. Hello?
Hola, pregunto por Richard Rossi.
Yes, speaking. Sí.
Mensajero. Paquete.
Paquete, sí.
Y estoy aquí en la entrada del centro comercial. ¿Dónde está el local?
Sí, Joe, I think. Sorry, guys, all the posts arriving at once. Yeah, let's continue from where we were. So, with the Triac, we have a circuit with a symbol like this. This is the symbol for the Triac, okay? And we have a gate. Now, because effectively we now have a diode in both directions, this will conduct both half cycles. So it conducts the AC both ways, okay? So we can't say anymore we have an anode and a cathode. So usually this is called MT1 or main terminal 1, MT2 or main terminal 2. It could have other denominations, yeah, but that's one of the common ones. Now, once again, we have the mains coming in, 220 volts, since I wrote 220 this time, yeah. And we have our load, and we have hot ground, which is really just the other end of the mains, the 220 volts AC, okay. And we can switch this. So to switch this, we again would use an Opto Isolator normally. Now, one of the ways we can do this, I also have to draw past this lot. Resistor, yeah. And here we could have, as before, an Opto Isolator with a transistor in, yeah, and that switches our gate. So we can have a circuit like that. When it switches on, it connects the voltage from here to here. It no longer needs a diode in here because in this case it would only use the positive half cycle to switch. Now it uses both, so we no longer need that, yeah. So we can do that, and then once again we can have our LED connected to safety ground and switched by some sort of controller, yeah. When the LED is on, this will conduct, yeah, and as long as the LED is on, same as before, as long as the LED is on, it will continue conducting. Once you switch the LED off, like in this one, what will happen is when it comes to the end of the half cycle, when it passes 0, it will switch off, okay. So we get the same sort of thing, but now we have the full waveform. And for example, switching it on here and switching it on here, you could now effectively have half of both half cycles, conducting, and now you have got a light dimmer. So as we move the switching point up and down, when we're conducting the full cycle, the light is on full. When we at this end, it's on dim, yeah, and that's how it's working. Now you'll sometimes find a variation on this, and this might be what we have. I'll have to check. So we'll just draw it again. It's basically the same circuit and probably a little bit less messy this time. So we have our Triac, yeah, we have our load. This is your 220 volts AC. This is your hot ground, which usually has a symbol like that, by the way. Here now we use a different sort of Opto Isolator. So this is called an Opto Triac, basically, yeah. So inside our Opto Isolator, okay, we have another Triac, and this is connected to the gate. Yeah, it connects to there. And again, inside our Opto Isolator, we have an LED shining onto the Opto Triac, okay? And this again is a resistor, this is safety ground, and this is to whatever control is switching it, CPU or whatever, okay? In this type of Opto Isolator, Because we use an Opto Triac here, it can be designed in such a way that no matter when you switch this LED on, this will always start to conduct at the 0 crossing point. So it only ever switches on at the point the waveform crosses 0. Okay? This, as I mentioned, stops clicks on speakers when things switch on and off. For example, we used to have the old lighting controllers on the mobile disco, and you would get effectively a spike when you switch the lights on. So we would use this type of circuit to switch them on at the 0 crossing point. It doesn't cause as much interference on the mains, basically. This thing, although I actually called it an Opto Triac, yeah, really that is the Opto Triac. This thing has another name, and you've probably heard it before, and it's called a solid state relay. Okay, that is a solid state relay. And back to where we started, I think the black thing on our circuit board may in actual fact be a solid state relay. Back to our circuit board then. I had a quick look on the internet, and Smith of Derby, who made this, are actually still going. They're still producing the equipment. But hopefully we can actually find something wrong with this. Otherwise, I may contact them and ask them if they can give me some advice or schematics. You never know. The worst thing that'll happen is they'll say no. And the second worst thing that could happen is they'll just ignore you. But nothing to lose, guys. So this is a transformer. We can see that. We can see we have mains in. We looked at this before. We have 2 fuses. We have a transformer. We have another fuse. Bridge rectifier. A large capacitor. This says 5 volts fuse. Now the transformer 0 to 9, 0 to 9, and this is probably a 5 volt regulator, like on the previous board we were looking at, the air hockey controller. That's probably a 7805 or something like that. This is obviously the brains of it. A little CMOS battery. I've checked this chip out. This is actually a 24C256 or something. That's an EEPROM. That's an EEPROM. I'm not sure what this one is. We have some switches. Then we have the display unit. And we have these clock connections. They all say live, neutral, live, neutral. That's all they say on them. These 2 are switched on, these 2 are switched off at the moment, if that's how it was set. No doubt they have 2 clocks. So let's have a look at this transformer and how it's wired up, because all this part basically is power supply. Yeah, this looks like the Opto Isolator Triac thing, maybe, possibly effectively a solid state relay. We can look at that as well. So we have mains coming in here, okay, and we can see the mains comes in here on this connector. That's these. This goes to the 2 fuses, so that's going to the 2 fuses, and coming out of the fuses, they're actually marked. So this says clock and this says power. So the power, I'm guessing, goes to this transformer. So this is coming out of the one that says power, and this feels like it's under here somewhere. So I'm guessing this is going to our transformer. Yeah. The other one, which says clock, goes across here, and this, if you look at it, is actually where it says load on this. We'll look at the part and see what it is, solid state relay. Yeah, that goes to there, and the other side of this, we can see it. So this is coming from the fuse. So this is coming from the fuse to there, and then the other side of that switch goes through all these, and this is these connections to the clock. So basically that switches the power to these. When this is turned on, we have power coming out. We can say that, yeah. Other side of the transformer, well, there's 2 windings. It's marked on the transformer, so no, that's a 9 volt, that's another 9 volt, yeah. 1 VA, and possibly have fuses built in, or maybe even kind of like resettable fuses. I wouldn't thought you have fuses you could get at and change, but maybe like a thermal fuse, I don't know. If you look at the windings on here, these are the 2, and look, they're wired in parallel. So the two ends of these windings are connected together and go to here, and the other two ends are connected together and go to here. This is the bridge rectifier. Yeah, and the other end of the bridge rectifier, I'm sure is there, and it comes through here. Is this the fuse? Yeah, that's the fuse. So we effectively have power from the transformer going through the fuse into the bridge rectifier AC, back out to the bridge rectifier AC, back to the transformer. And the two windings are in parallel working together to double the current. Yeah, so we get effectively double the current. Little inductor here, probably just a filter. The bridge rectifier plus minus, you can see it marked. That will certainly go to this capacitor. Yeah, there's the capacitor. There's the bridge rectifier. Oh, look at it, comes through our little inductor. So the inductor and the capacitor are effectively the smoothing circuit. And then that will go to our voltage regulator, which is here. And that then powers all this circuitry. So that's basically how it works. Now we have some switches here. Start, stop, clock. Start, AT, whatever that means, advance. This is for setting the time, I think. Next, test. So the first thing you've got to think is, what's this thing actually do? I mean, obviously this can switch to here. We can see where the input's here going, and they come up here. There's also another Opto Isolator here doing something, and I've got a good idea what it's doing. Yeah, I think. I'll tell you what I think this is doing. If you look, effectively, this is all the high voltage side of the circuit. Yeah, this is the high voltage side. And then this is all the low voltage side. And this Opto Isolator is connected from the high voltage to the low voltage side. Yeah. The other end of the Opto Isolator goes, well, possibly to this switch, but into here. Let me tell you what I think this is doing, and this is all supposition and opinion, yeah? But this is what I think it's supposed to be doing. Basically then, we have live and neutral coming in, okay? Live goes through a fuse, okay? And it goes into our transformer, which comes back to neutral, yeah? The transformer's actually got two windings on it. On the secondary, 9 volts each, and they're actually wired in parallel. So this one is connected to here, and where are we going to draw it? Yeah, we'll draw it this way. This one is connected to here. Okay, so the two are in parallel. So here we have 9 volts AC. That comes into our bridge rectifier. I won't bother to draw the thing with the 4 diodes. I've done it before if you want to look it up. Plus minus comes out through a little inductor, big capacitor, and this is our 5 volts. Sorry, this is 9 volts. It's probably actually giving more like 12 volts DC, probably, because it's giving you the peak voltage, not the average RMS, which is this. That then goes to a voltage regulator, which I'm pretty sure, although I haven't looked it up, is a 7805. Positive 5 volts, 1 amp regulator. That's what I think it will be. We can check in a minute. Okay. This then is effectively as ground. Okay. And this is our plus 5 volts supply. So we now have a controller, the microcontroller, that big chip, yeah? And coming into it are some switches, which obviously can read the switches to control various things, yeah? And this controller is powering our solid state relay, if you like. Okay? So, again, we'll look up the port number in a minute, but this is what I think we have. Safety ground. Okay? I'm guessing it's a Triac. Let's say we'll look it up. Could be a transistor. Okay. That's that black thing we can see. What port number is it? It says cried on. Cried on. Okay, and that's a D. It says cried on, and it is a A0241. A0241. That's that thing. This is now switching the power, the live power, to the clocks. 1, 2, 3, 4. To the clocks, yeah. And then the other side of the clocks is going to neutral. So the other side is neutral, which is connecting back to here. Yeah, that's neutral. And this is being controlled by our microcontroller. This is LED, okay, shining light onto that. Now you'll notice there's another Opto Isolator, and the other Opto Isolator, I'm guessing this one's a transistor, I don't know for sure, but I'm sure you'll find the other Opto Isolator is here, okay. Safety ground. This neutral, if you like, this is our hot ground. Okay. And this, which is this one, there's a couple more diodes around here. Yeah, you see them there? I think you're going to find that this Opto Isolator connects either to here or to here. If it connects to here, it's going to do it through some high value resistors. Now I don't specifically see any. Let me see roughly where it's going. So yeah. I think this, one way or another, is connecting to here. The AC, yeah, and that will be going into our microcontroller. And I'm sure what it's doing is this LED, okay. This is AC, yeah, this is AC through a rectifier diode. So here we get the positive half cycles, yeah. There's no capacitor on here, it's not smooth, and I'm sure as the half cycle starts to go positive, because we have a diode here, so the negative halves are being discarded, it turns this LED on, yeah, and that turns this transistor on, and that signals the microcontroller. And this is a zero crossing detect signal, yeah. So as I was showing you on the Opto Triac, this tells the microcontroller when the AC voltage passes 0. Yeah? And this can switch the power to the clocks. But if I've got this right, what I think it's doing is something like this. The clocks need power to go round. Unless it gets a pulse of mains which steps it forwards, it might do. So it might be that there's like a stepper thing inside the clock. So effectively it just switches on when it wants to step it. A cycle, maybe. And then it switches off again. And a cycle, maybe. Yeah. And each one of these, it does it once a second. Yeah. One each second. Yeah. Maybe. This is supposition. Maybe, yeah. If you want to step the clock forwards, it does it 50 times a second, so it effectively goes round fast. Something like that is what I think it's doing, yeah. You can start the clock by setting the pulses. You can stop it. This is probably a set where it moves forwards. I'm not sure exactly. Maybe you can set something on here so it knows how many pulses to set. I'm not sure, but I suspect it's doing something like that. And if it's not doing something like that, it's doing something like this. So effectively, going to the clock is AC. Yeah. Okay. And this controller can effectively remove, by switching this off at the right point, it can remove half cycles. Yeah. So you can end up with something like this. The mains is coming in, and then all of a sudden the controller switches off this positive half cycle by turning that off. So that's missing, yeah. And then the mains comes back again. We'll have to draw it a bit longer. And at some point it can switch off again. So for example, it switches off the negative half cycle. Getting messy, isn't it, this? Positive half cycle missing. Yeah. Negative half cycle missing. So effectively your clock would have a continuous power, but by switching off these half cycles it can detect, and that effectively is like a logic 1, and the negative half missing is like a logic 0. Something like that maybe, and then there's another board up by the clock which it can detect those. I'm not sure. I think it might just be sending the pulse, because the clock has to move once a second basically, yeah. So I think it might just be doing what I said in the first place. It's just effectively sending a pulse for a couple of cycles maybe, then nothing a second or so later, something like that. Yeah. I'm sure you guys can suppose various other ways in which it works, but I'm confident that's what we've got. So how can we test it? Well, we can look for short circuits on the output of here. Yeah, we can check things like the opto isolators if they've got shorts or anything like that. If we can't see any obvious shorts, we can power it up and see, do we have a 5 volt supply here? If we have, we can say all that is working. Yeah, we can then measure here and see where, or rather look here, and we should be able to find these half cycles, the zero crossing thing. Is that actually working? Yeah. The display might light up. I mean, the microcontroller has a display. We can see if the display lights up. If it lights up, we can probably assume the microcontroller is working, and then we can have a look here to see if it's driving some sort of switching into our Opto Triac, if it is. And we could also, for example, put like a small mains light bulb on here, give it a bit of a load, and see what they do. Yeah, let's see what they do. So that's what we have. So let's have a look at our circuit board now. Get into the comments below if you can think of some other way this is working with the information we have, or maybe you can find more. Yeah, and let's see if we can find out what's wrong with it. First things first then, short circuits and testing the fuses. So we have a fuse here. This is okay. Let's undo the other two. I don't know which fuse blew, by the way. I could ask the guy who sent me this. No, it's coming out still a bit stiff. We have 2 more fuses. This one reads okay. The meter's not exactly zeroing. Well, actually it is, but these fuses are low value, so they read a little bit of resistance. That's normal for very low value fuses, to be quite honest. This one says 500 milliamps. Yeah, the other one was only 160, and the one up here was also 160. So that's why they read a little bit of resistance. So that's okay. We can look on the output of our voltage regulator. It's the 7805. Yeah, you probably can't see it, but it's a 7805. So 7805 positive regulator. Pin 1 is in, pin 2 is ground, pin 3 is out. Let's have a look. So ground is pin 2. This is in. No, I tell you, this is out. And there's no short there. In, there's no short there. We can actually go to ohms range. yeah, kilo ohms and climbing up, yeah. Kilo ohms and climbing up. So we know the fuses are okay. We know there's no short on the output of the 5 volt regulator. While we're here, we should probably be able to test the bridge rectifier. Now this might be a bit difficult because it's connected to the actual transformer winding. So the two AC inputs here are connected to the winding. So what we'll do is we'll remove the fuse. Because otherwise, across the two AC inputs, we would just see a short. On the other side of the fuse, you'll see it, yeah? Almost a short. So we'll disconnect the fuse. Now we can measure the bridge. So we'll go from this AC input first, this one. It should connect to one of the terminals through a diode. And that does, it goes to there, yeah. It should then go from the other input to the same place. And it does, yeah. If we reverse that, we should have nothing. Okay, so with the black to either of the AC inputs, we see a diode. Okay, now let's go to the other side. So this is the other output, and this works the other way around. So with the red to either input, we should see a diode. Diode, diode, yeah? And then the other way around, we should see nothing. Okay? And there isn't a short across the bridge rectifier. You'll probably see the capacitor charging up. Yeah, there, see? That's why it went 0 and then started to climb. Okay. So there's no shorts in our bridge rectifier or open circuits. That reads okay. Do we have any shorts anywhere else? Well, really, without a load connected, you can't prove it. I mean, we can just check on the output of this to make sure it's not permanently switched on. So this is our Opto, whatever it is. Should read open both ways. Reads open both ways. This is the LED side, so you expect it to give a reading in one direction. 1. Just reading open this way. No, 639. So I can't directly measure that in circuit, to be quite honest. We have the other Opto Isolator here. So the input is going to come in one of these pins somewhere. Well, there's no shorts there, that's for sure. This reads a bit like an LED, 105, what's the other way around? Open, so that reads pretty much okay. The output looks like it's here. Well, it's reading a junction, it's not short. That's reading nothing. And we have some diodes down here, so while we're at it, let's test all the diodes as well. Just looking for shorts or open. So that reads like a diode. This way reads like a diode. Same way reads like a diode. So they look okay. Another diode over here, so we might as well test it. Reads like a diode, okay. So that's all the components I can really test here. What we need to do now is power this up. To power this up, I'm just going to use this. I made it, it's very simple, just an IEC socket connected to 2 bits of wire, and this is really handy for powering stuff like this up. You should make one of these. Very simple to make and really useful. We'll just fasten the screws down. Okay. This one's like a bit stiff going in. It's got it. That's a good, easy way to connect your wires to anything like this. So make one of these, put it in your toolbox or your stock of bits. Let's get a power lead and power this up then. We know there's a high resistance across here, so we don't need to put a light bulb current limiter on. And we'll find out then if this actually lights up. Does it do anything or is it dead? I have the power lead attached, it's not plugged in. Yes, just one other thing I will just quickly check because I neglected to do it. And that's just the voltage on this sort of CMOS type battery. Looks like this is the terminal from underneath it, where the track's going. 3.23 volts, so we have a good battery, yeah, that's fine. What's it do? Power on. Well, it doesn't do anything. It's basically dead. It doesn't power up. Let's see if we've got any voltage supply in this. Easiest place, or rather say easiest, best place to check first is actually on the output of the voltage regulator. And it looks like we'll have to turn this upside down to do it. I've got it switched off at the moment. Okay, so we can see here is our voltage regulator. This is the negative end of the capacitor. It goes to the negative end of the bridge rectifier, you can see there. And the middle pin of the voltage regulator. So that's the best place to check. So we'll just get here. All the high voltages over there, not anywhere near us. Switch it on. What do we have? We have 5 volts. Yeah, we have a 5 volt supply. So this must be like 12 or 9 or whatever's coming in. It's got to be there. If I've got an output, I must have an input. Well, strangely enough, it doesn't read anything. Okay, so now it's gone off altogether. That's interesting. Half a volt. Switch it off again. Let's go across the capacitor, which is basically the same place I was just measuring. So this is here to here. Switch it on. What we got? Only half a volt. Okay. Well, we've got AC coming in from the transformer. Let's have a look. Did the fuse blow again? Because I had 5 volts originally. Select. Okay. This is AC coming from the transformer. Nothing. What have we got going into our transformer? Practically nothing. I think the fuse went. Switched off. That'll be this one. I mean, this fuse is still intact, we can see that. Well, something else strange is going on. I mean, it's one or the other, yeah. Looks like the fuse went. So something's drawing too much current from this by the looks of it. There's the fuse blown, yeah, for sure. No meter's working. Fuse went. Okay. I'll obviously replace the fuse. Let's take this fuse out. And then the transformer is just being tested on its own. I don't suppose there's a problem with the transformer. Something you must buy is a good stock of fuses. You can see I have all these, and I have these go up to about 1.6 amps, and then I have another box the same with all the higher ones. So I've got them all labelled up, as you can see in this little bag. 315, 125s, 250s. These are 160 milliamps. The label's kind of back to front, but these are 160 milliamps, which is what we need. So this is something you need to buy as a good stock of fuses. Okay, I'll keep them on one side in case I need any more. So let's replace our fuse. Actually, I should have stuck it into this end first, probably. It's gone in anyway. Replace our fuse. Okay, let's remove this fuse. So now basically we have no load on the transformer, so the fuse shouldn't blow, and we should still be able to check if it's working by measuring directly across the secondary. So let's go with that. We have a meter which needs to be on AC volts. Okay, switch it on. what we got coming out of our transformer now. So we have nothing. We have nothing coming out of our transformer. What's going into it? Should be the mains voltage. 4.7 volts. A fuse gone again. Let's have a look. Ohms range. No, I think it has. Yeah, fuse is blown again. So we've got no load on the output of the transformer, yet it's still blowing the fuse. I'm guessing the other fuse is probably okay. Yeah. So why is it blowing the fuse? Well, one possibility is we've actually got shorted turns in the transformer. Let's have a look again to be sure it's switched off. So the output of the transformer, you can see one end goes to the bridge rectifier, and the other end goes to the fuse holder. So we've definitely disconnected the output. This also goes to here, which is a little diode, which goes to our Opto Isolators. That's what the Opto Isolator does basically. That's where it monitors the zero crossing. So there's no output on the transformer. Why would it blow? Well, could be the transformer. Say if you get a shorted turn in the windings, that will do it. But there's a few other components across here as well. And in particular, there's one here. So you see we have one end of the winding. Yeah, we have the, I'll just unplug from there. We have one end of the winding. We have the two tapped together, and then the other end of the winding. And from here to here is a component, yeah? Can you see it there? And that is this thing. And this, although it looks like a capacitor, is probably a voltage dependent resistor. So effectively this goes short if you get a surge or over voltage. Now I didn't measure any shorts across the input, but that is wired across the mains, and if that's breaking down or something, it might be what's causing the problem. You see there's another one here. Let's unsolder that and let's see what we have. Here's the components. I've just had a bit of leaded solder. I've switched the desoldering gun on. That's where you can probably hear the vacuum machine. But we might just be able to lift this out anyway. So if I just put my finger against one edge of it and heat up this end, it probably just move. It's not moving at all. Maybe I'm in the wrong place there. Maybe it's actually here. Let's have a look. No, it looks like this is it. Let's get the vacuum tool. Well, let's hopefully desolder it. Just checking it hasn't clogged up. Yeah, that's desoldered. Let's just see if we can get it out without breaking it. Doesn't easily want to give it up. Let's see if we can just hold of it like so. With the soldering iron again and see if it will just effectively come out. Yeah, I felt it move. Okay, so that's coming out. Going the same on the other end. Yeah. Still not quite out. One end of it is out. Now it's out. And now we might as well just use this and clean the holes. Ready to put that back in again. So here's the blue thing that looks a bit like a capacitor, which I'm sure it isn't a capacitor. Let's have a quick look at the markings under the microscope. So there's the component. You can see GNR 14D431K, and then it says VDE, but I think it's actually a voltage dependent resistor basically. So let's look for a data sheet for that. We can see what this actually does, and I'll explain what it's doing in this circuit. And hopefully here is a data sheet. So there it is, metal oxide Thyristor. A Thyristor is basically what I call it, a voltage dependent resistor. So the resistance depends on the voltage across it. Let's see if we can find our model. 14 is the size, millimeter. Yeah, D is standard. 241 is the voltage, 240 volt. So this basically triggers at 240 volt. If it goes above 240 volt, it effectively becomes like a short, or certainly a low resistance. And ours appears to be faulty. So let's have a look if we can get this thing to work without it, because this is basically just a protection device. I'll show you one little schematic. Here you can see the metal oxide Thyristor, or MOV, or voltage dependent resistor, is used in transient protection of electronic circuits. So it is a safety device. It's not part of the circuit from an operational point of view. It is part of the circuit as a protection device. So this only does anything in the case of too much voltage coming in. Now, we know that this failed due to a power surge, and a lot of other stuff failed as well. So it's quite likely that's why this Thyristor has failed. The Thyristor is actually connected to the input of the circuit. So we have live and neutral going to the primary of a transformer via a fuse. Okay. And the Thyristor is actually connected from this side of the fuse across the power like so, yeah. And it has a symbol like this. Okay. So that's where the Thyristor goes, and the idea is that if more than the rated value, in which our case was 240 volts, appears across here, this conducts and effectively blows the fuse, and it usually blows the thing as well, or damages it. So in this case you normally have to replace it. They usually go short circuit. It looks like ours hasn't gone short, but it's in some way blowing the fuse, like it's breaking down under voltage. That's A, to protect the primary of the transformer, and B, to protect whatever's connected to the output of the transformer from too much voltage. So if you get a voltage spike here, or induce a voltage spike into here, which will go into the low voltage circuit. So that's what the thing is for. When these fail, they normally blow up, and you can see in our case, in actual fact, it has failed. Can you see where it's split down the side there? Let's get the focus on it a little bit better. Yeah, you can see, yeah. So this is what happens to them, usually a bit more spectacular than this, but you can see it's cracked, it's broken, it's blown, yeah? Because this is a protection device, we can actually basically connect our device with this missing. We can take this out of the circuit and power it up. So we no longer have the protection, but we can at least test to make sure that nothing else has gone faulty in our circuit. And then obviously I need to replace this before it goes back to the owner if it's still working. So to do that, I'll just do two things. First of all, I'll actually check that my mains voltage is not above 240 volts for any stupid reason. It is coming through a Triac. It might possibly be, but I doubt it. But let's see. And If it isn't, or I can even turn the variac down a bit so it's definitely below, we'll connect this up and see what happens. So I'll leave this out at the moment. We don't actually need it to test the device. Here's our mains plug. The mains is off at the moment. Let's just do a basic check. And you can get varistors of all sorts of voltages, by the way, not just mains voltage. They're common, but it's quite possible to get them for lower voltages as well. Let's connect our probes to our mains lead if we can get a good connection. These are probably not very good leads to do it with, actually. I'll find something a little bit better. Okay, let's use these leads. I'm on volts AC. I can poke these down the lead. Just hold it quite safely with one hand. Switch it on, and then we should have, well, 240 volts or less here. Let's see what we have. 228 volts. So there's nothing wrong with the main supply. It's quite simply that this has blown. So I'm going to power it up without it, and let's see if the thing comes on now. I'll just make sure I have two good fuses now. So this is the one of them. Yeah, that's a good one. And then the other one is here, which is also a good one. Let's try this again. We'll put the power in here, just make sure there's nothing under here, bits of wire and such like. Move that out of the way. Power's off at the moment. Connect the power to this. And let's switch on and see what it does. Well, that's what it does. Okay, so it's working. I've had a look at my stash of stuff, and I have some varistors, but none of them are the type that I want. Although this is effectively a non-essential device, the operation you can see, it's also a safety device. So really, especially with something like this, which is a commercial item or industrial item, you need to replace this with the correct type. Yeah, okay, it's working, you can see that, but this is there for a reason, and this protects all this circuitry if they get another power surge. So I'm going to get the correct type for this for the reasons I've just mentioned, and I hope you guys agree with me that although it means waiting for parts for something that could make work, that is really the only way to actually complete this job. So let's see how much these would be to buy some. They actually come in a pack of 10 or 20. This one is saying delivery around the middle of November. I mean, it could be a little bit quicker. So we're looking at parts a bit over €3. I will let the buyer know, but I will order these anyway because I know he's going to say yes. I will charge him my standard repair charge plus the parts for this. So I think we can actually declare that one repaired. And there we have it, guys. So this one is definitely repaired. I'm sure the customer will be very happy with the cost of the repair on this one. If you sent it back to the manufacturer, I'm sure they would charge you a lot of money. I charge €45 plus the cost of parts. Okay, the owner pays the postage, but I think that's a very reasonable price to do this sort of repair job. It wasn't too difficult. I hope you've also learnt something very useful here. So with this type of thing, look out for these blue components that look like capacitors, but they clearly are not. You'll find them around the mains input normally, which they were here, and you can see this one's visibly damaged. Even if it wasn't visibly damaged, I would have removed it and tried it without it, because on the odd occasion they will just fail. But to be honest, in my experience, when they fail, they do it like this. Yeah, they tell you that they failed. Okay guys, hope you enjoyed that one. Quite a short video, another interesting PCB. I know a lot of you like this sort of repair work, so I'll definitely be doing more of this when I have the opportunity. Okay guys, see you all soon on another Learning Electronics repair video. Ciao for now guys.